All right, let's start. Do you have any questions? Okay, so let's pick up where we left off last time. So before the midterm, we were discussing, right, change of measure. And so let's just remind ourselves one more time, right? So the framework is that we start out, right, with the risk neutral, the physical world, right? This is physical, meaning, right, this is how the stock actually behaves, or how we see it, right, empirically behaving, and then empirically behave, and then, right, we know that for the pricing equation to work, right? So basically, okay, I'll write down later. Right. So this is risk neutral. So it's not risk neutral yet, right? So one more step. This is risk neutral, right? So basically, right, when it comes down to it, you know, the difference is that in P, right, WT is a Brownian motion, and in P tilde, right, W tilde T, which is, right, this guy, is a Brownian motion. Okay. Now, but then, right, that's just sort of like a mechanical way to look at this, but it's fine. Now, I want you to kind of know this, right, that in general, doesn't matter what model you use, okay? In general, a risk neutral, right, probability is such that, right, the pricing equation works, meaning that, I guess I'll make it the most general. Okay, so what are we saying, right? So obviously, right, this is just the pricing equation, right, discounting the future value into the current value at time little t. For all I here means that we could have more than one asset, right, more than one stock, or, you know, it could be bond, it could be foreign exchange rate, right, whatever. So basically, for all assets under consideration, right, the pricing equation must work that way. So you must be able to find some probability, right, such that when you apply the pricing equation under that probability, right, it works that way for all assets that you're modeling, right? Of course, right? So the whole point of pricing is this is still modeling, right? After you model, then you will construct some sort of like, you know, then for whatever option, right, which is basically just, you know, if it's your European style, then it's just a function of, right, the value of all these guys, for example, at time t. And then you can use the same, right? So then the pricing equation would be this. Okay. So there you go. Actually, that's pricing, right? The pricing in a couple lines. So in other words, right, this is basically the modeling part, or the definition, right? This is the modeling part. Okay. And after you finish your model, you make sure that everything is fine. You make sure that there is a risk-neutral probability in your model. Then, right, whatever asset you can come up with, whatever derivative you can come up with, right, you can use the risk-neutral pricing equation to price it, right? So this step becomes mechanical. Now, I don't want to say it's mechanical in the sense that, right, if you look at, say, exotic option or American style option, or there are other financial considerations, then the pricing, right, mechanism must change. But that has to do with the structure of the option itself, right, which we'll talk about later. But in terms of the scheme, right, of risk neutral pricing, this is how it works, right? You write down the model for your asset. You look to find if you can find a risk neutral probability that does this. So also, right, you can take this as the definition, okay? Definition of risk neutral. In other words, risk neutral probability doesn't have to be this, okay? Is this one because we are looking at the simplest Black-Scholes model. Yes, if you improve on this model to include, right, let's say 2 Brownian motions, or you include a Poisson process, or you include, let's say, changing volatility, right, like a Heston model, then of course, right, P tilde doesn't like require only this, it requires much more, it requires something differently, right? So all in all, this will be the most abstract framework that you can use. And then from here, right, you actually, from here, you unravel it back to see what you need, okay, to require your risk neutral probability to satisfy. Is that okay? Now, question, any question? Now, then, right, then comes the mechanical question of how can we change measure, right? And so at least it seems like, right, that at the basic level, it's like you're adding the drift to a Brownian motion and require that you find another probability such that, right, that Brownian motion would drift. Now is a Brownian motion, right, under that new probability. So the mechanics, or the, I don't know how to say this, the main theoretical tool, right, is this so-called, right, change of measure result, or the Sarnoff framework, right? So change of measure framework can also be viewed, right, from a broader point of view, which is this, that first of all, you just define change of measure like this, okay, for x in ft, okay, zt positive, non-negative, and zt is 1, okay, and 2, right, conditional will be this. Okay. Again, this is broad, meaning that, right, doesn't matter, as long as, doesn't matter what kernel you use, as long as you use, some kernel that satisfies this condition, then you have a change of measure framework. All right. And now, right, then the second one will be, well, we don't want just any, right, good old change of measure framework. We want it so that, right, the condition is satisfied. Then comes, right, the Sarnoff, where it says that, well, if you want, right, W tilde t, right, which is W plus theta times t, then the change of measure kernel you want to use, right, would be the martingale, right, the exponential martingale associated with Wt, right? So here, this will satisfy that W tilde t is a P tilde Brownian motion, and W, right, while W is a P P by motion. So there, right? So Gasanov just makes this more specific. In other words, right, if you want to accomplish this purpose, then, sorry, if you want to accomplish this purpose, then this is what you use. But on the other hand, right, like I said, change of measure is much more general than this. And, we will discuss like Poisson process later on, and you see that it doesn't have to exactly follow, right? I mean, this kind of kernel, because it's a different process. All right, so there's that. And of course, you can generalize, right, Gasanov for more than one Brown motion, like your homework, right? So you can generalize this to more sources of noise, right? Again, this is just the beginning, meaning it gives you an idea of how to construct things with the simplest Brown motion model, right? But you can definitely extend this to incorporate more complex model. All right, question. So then the next thing, right, is about no arbitrage, right? And completeness of the market, right? So no arbitrage, I guess there's an English definition for it, right? But we'll just say that there exists no portfolio, right? There exists no portfolio pi, right? Such that pi of 0 equal to 0, and p of pi t non-zero is 1, and p of pi t positive is positive, right? So again, right, that's a mathematical thing. But what it says, right, is kind of clear in your model, right? So pi here is a value of a portfolio where you combine, right, all the assets, and then, right, the derivative you're looking at, right? Whatever it is, whatever it is that your model is talking about right now, you can combine them into the portfolio. So it says that you cannot combine them in such a way that it costs nothing, right, to form the portfolio, but in the end, right, you will not lose, guaranteed, and then you will win sometime, right? By the way, this is stated under the physical probability, but because of equivalence, right? Because of the market being equivalence, you can easily replace that with P tilde. Sorry, not the market, the probability being equivalent, right? So that's actually the whole one point of the risk neutral probability, that the argument of no arbitrage, right, under risk neutral can be translated back to the physical. Completeness, right, means that any derivative can be hedged. Well, what does it mean mathematically? What it means is for all, I think so I'm going to state it's only for European options, but because the hedging way looks different for American option and exotic option. But anyway, right? I guess the idea is, the idea is clear, that if you have a derivative, right, constructed out of your assets, then you can find, right, portfolio pi, right, such that pi t is equal to vt. Well, what does pi have to do? Well, the only restriction on pi is it must be consistent of the tradable asset, right? So in other words, these are the number of shares you choose to hold, right, in asset Si at time little t, and this portfolio pi must be self-financing, right? Self-financing, we talked about it before a little bit. Basically, self-financing means that you cannot insert money into the portfolio at any point. You cannot take money away from this portfolio at any point, right? You form it, and you can move, right, asset, right, from one stock to another, right? But you cannot take cash in and out. Anyway, right? The point is, I don't want to like go deep into this. Trust me, these can go really deep. You can spend like the whole class talking about these kind of things. I mean, by whole class, I mean not the whole lecture, the whole semester. I don't want to, right? Because it's sort of like deep into a theory, and frankly speaking, in practice, right? People don't really worry about it too much in exactly this language. But at least you should know a little bit, right? What I want to say is this, right? How is this? By the way, these conditions are very sensible. Okay. Now, of course, like I said, people don't worry about too much in practice. In a strict form, meaning like something like this strictly, I guess I have not come across anyone outside academic that really worry about this. But in the weak form, meaning that something similar to this but weaker, or something like this but weaker, people definitely care about, right? For example, delta hedging is part of this. All right. Some sort of, right, no obvious arbitrage must be there, right? Otherwise, like, how can the market function? Anyway, right, so you should at least be aware of what these are saying, right? Keep in mind that they may not be perfectly held out there, but what they say and what people look for is kind of sensible, right? It will be there. So what I want to say though, right, these conditions, how they are connected with the risk neutral probability. By the way, I think I forgot already, it's been a while. A market that satisfies both conditions has a name. I think it's called perfect market or something. I forgot, but who cares, right? Basically, there's a name for both conditions together. So here's the thing. You could have a market that satisfies one condition, but does not satisfy the other, all right? So it's either or, it could be. It doesn't have to be both at the same time. Now, anyway, right? So the result that you want to know is this, and I want to kind of just talk about a little bit. No arbitrage is equivalent to there exists a risk neutral probability. And completeness is equivalent to the risk neutral is unique. So it's kind of funny. I mean, in a sense that it doesn't make sense to discuss completeness unless you have, right, something to talk about. So there you go. But I guess, in some way, right. So they're kind of in the different domain. If you do math, right, especially like linear algebra, you would know. One is about existence of solution. One is about uniqueness of solution, and they're kind of complementary. They're not really, in the same domain. So they're not mutually exclusive in some way. But of course, like I said, logically speaking, right, you don't want to discuss uniqueness unless you have some existence to begin with. But anyway, right. So how does this connect? I don't want to bring this down to home a little bit, right? How does this connect to the whole Black-Scholes framework above? So let's investigate again, right? And then we have, so this is physical, right? And then we transfer like this. Okay, and we call this W tilde. So this is, classical Black-Scholes, right? So is this model, right, arbitrage free and complete, or is this market, right? Is there any condition that you need? So classical Black-Scholes, right? Is it arbitrage free and complete? Is arbitrage free? Okay. You want to say something, Kareem?
Yeah, I was gonna say it is, or it is no arbitrage because there exists like a risk neutral probability, but I'm not sure if it's unique.
Right. So first of all, right, there exists a P tilde. That's correct, right? Because of Besanov, right? Now, again, I guess Kareem's confusion is understandable, right? But then you want to go back to this model and try to think of how we convert from physical to risk neutral, right? And in the sense that, right, for risk neutral, we must have R here, right? We must have R here, right? And then that forces this to be this. In other words, is there any other way that you can come up with this model with a different W tilde, right? So for uniqueness, the question you ask is there any other way that you can define W tilde? Besides this way? Well, the answer is no, right? And again, it might seem strange if you just see this, but you've seen this week's homework and you know what happens, right? It will be clearer when you look at more assets, right? But if you look at one asset, it's kind of like it's too reductive. But okay, we'll look at the multi-asset model example right after this. But you just kind of look at this, and there's no other way you could define the W tilde T, right? Because the reason is because this is force, right? The R STDT is force. The drift, right, of ST must be R STDT, right? And so basically, let me say this, right? So basically, because, right, the way you look at it is like this. You require, hold on. Basically, you require this. Agree? So where I kind of pull the discounting term, big T minus small t, right? I bring it over here. There's a reason for that, right? Because this is, again, right, this is the price, this is the requirement, right? This is a definition. This is required, right? For risk neutral, right? But notice that what does it say? It says that E minus RT ST is a P tilde martingale, right? This is one of those rare times where you want to pull out the martingale framework, right? Now, if this is a martingale, what does that mean? Well, we can pull out our Ito's formula, right? This is also what Ito's formula is used for. So it says, right, this is going to be minus R, right? So there's an E minus RT all the way outside. And you got minus R STDT, right? And then plus DST. Agree? So what do I want to say now, right? And so what this says, right, is and what does a martingale, right? So what does a martingale, being a martingale, required? Being a martingale requires that basically the drift, the change, right, the differential must be a martingale itself. So this must be this part, okay, must be D of some martingale. Okay. It comes from the fact that the only way you can retain the martingale when you integrate back, is for the change itself to be a change of some martingale, right? So that's all it's saying, that the change itself must be a change of some martingale. Well, what does that mean? What that means is exactly what I was trying to say above, that that means that the change of the stock, right, must cancel out this part because this part is not a martingale part. So that means that dst must be rst dt plus some d of some other martingale part. So maybe another different martingale, right? And that martingale part is exactly this part right here. Do you understand? So again, right, it's a little bit abstract argument, but it's trying to tell you that this part is forced if you require this to hold. And if this part is forced, that means the Brownian motion is forced. Okay, so that's all you need to know. So that's what it means, right? There's no other way. So this market is arbitrage free and complete. Yes, on both. Okay. We'll go back to this martingale argument later, right? But it is important, right? But kind of for now, right? Just try to understand that basically that for something to be a martingale, when you differentiate it, right? Basically, the derivative must be also a change of martingale. All right. And for that to happen, right, the drift must be canceled out, leaving you with, right, literally a martingale. All right, so too much of that, right? So this model is arbitrage free and complete, but any condition, is it always true that the Black-Scholes model is arbitrage free and complete? Well, you may not think of it as much of a condition, but you need this. I mean, you can do sigma non-negative, right? But not non-zero, but you know, traditionally sigma is always positive, non-negative. So basically sigma cannot be zero. All right. Why is this so? What happens if sigma equal to zero? If sigma equal to zero, then starting out, right, with the physical model, you see that you will have this. Right? And there's no way for you to change it, right, to the risk neutral world, right? Because this cannot be derived. Yes. Again, right, that sounds trivial, but trust me, it makes sense later. But also, actually, just from a common sense point of view, right, why is this problematic? So that you understand, right, from a modeling point of view, why is this problematic?
It's not random. It's not a stochastic process.
Say again.
It won't be a stochastic process.
Yeah, but that's not where we're getting to, right? That's too pedantic. We want to get to very basic. In terms of our model, right? Why having something like this is. So I want you to understand we are really talking about market here, right? Even though we do a lot of fancy math, the finance is in the background. So when I tell you the answer, it will be so obvious, but still want to see if you can see it. Yeah, but why is that a problem? Yeah, why is that a problem? You are getting close, but why is that a problem? Notice, right? When sigma equal to zero, what condition will be violated? The existence and the uniqueness. No. So first of all, right, when sigma equal to zero, I want you to see that there is no existence, right? Because you cannot define a risk neutral one. So what that means is we will have arbitrage, right? Pure and simple, if you trust the theory. But is it clear that we have arbitrage here? Yes, it's clear because we have two cash accounts. Two money market process. Where's the other one? The other one is the one that we never really even say. Right, the bank account. So again, right, you see there are things that we leave unsaid until it comes, right? So here, there is always this kind of thing, right, in the background, because cash, right, earns interest rate, right? And if mu is not equal to R, which is the implication here, then, right, you can borrow and lend at different rates. You know what I'm trying to say? So that this will result in an arbitrage opportunity. Is that clear? So the message, right, is that actually is very simple. If sigma equal to 0, right, you can see very quickly that yes, indeed there will be arbitrage. No abstract math is required to see that in this case, that is true, right? And so that's why for the model to be proper, sigma must be non-zero or sigma must be positive, right? You cannot model two money market process like this. Okay. We cannot Fatima. How can we? You have no W tilde, right? You cannot define any Z, right? Because the Z in this case is connected with the theta. There's no theta, right? There's no, basically the message is when sigma equal to 0, no market price at risk. And you need market price at risk to define a risk neutral. Well, by market price at risk, right, I mean this, the Sharpe ratio. You understand? So that's the message, right? Market price at risk is connected to risk neutral probability and vice versa, right? It's actually pure and simple like that. When sigma equal to 0, you have no market price at risk, or as the above, right? You guys say that the stock will always rise, blah, blah, blah. That's all boiling down to exactly. There's no price at risk. There's no risk. Therefore, right, you have a weird situation, right? Again, it's super simple, but it just tries to demonstrate, okay, that framework that is actually consistent. Now, any questions so far? Now let's make this less trivial, right? And exactly this is your homework. So you see that, right? This will make much more sense when you look at multi-asset model with multiple, right? Sorry, that's one. Okay. So first of all, right, just so that you kind of, so here W1, W2 are independent Brownian motion. They don't have to be. They can be correlated if we want to model it that way. In other words, we can model a market with correlated assets. All right. Here we just make it independent to make it easy to look at things, but you definitely can make it correlated. So first of all, right, just so we understand things, right? What's the volatility of S1, for example? If you look at this model, what's the volatility of S1? am I doing a legitimate model, or this model is completely whacked, meaning that it doesn't fit into the framework of what we did before? Well, again, right, this is where, like I said, right, your finance, you have to come back to your financial root, right? We can do fancy math, but if you don't understand the finance behind it, it becomes a nonsense very quickly. Notice, right, this is still that model. That we kind of talked about at the beginning, right? Of course. Right? And so similar to the other one. What do we call this? What is this?
The return.
Percentage return, right? Yes. And so volatility is what? Volatility is the variance, right, of the return divided by the rate, right, the unit time, right? So here, what can you tell me about the return? The return here, according to this model, is distributed like what? Is it normal, right? With what kind of rate? What kind of mean? This is the mean. What's the variance? Times dt, right? And where did I get this? Because these are independent normal, if you will. Agree? So this will be so the volatility is square root of this guy. Is that okay? Is that okay? So again, right? If your finance is okay and you know what you're reading, this is no different, at least from the distribution level, from the Black-Scholes model. Yes, it's the same thing. It just tries to say that where the normal comes from is a bit complicated, right? It gets mixed between two noise source. But okay, so what, right? In terms of distribution, as long as you understand the concept, it's the same thing. Okay, so far. So I want to say that again, right? That this is indeed just a easy extension of the Black-Scholes, if you will, right? Every concept we talked about still makes sense. By the way, right? For example, if you look at the log return, right? What's the rate? What's the rate of the log return? Right, just to show you that we can extend our framework to beyond, right, the simpler model that we want. Not that we will do this exactly, right? I just want to show you the sky above, right? Then we go back to the simple model. But how do you find the log return here? Well, so right, apply Ito's, right? But here, Ito with more than one Brownian motion. So how does that work? Now, I did not tell you, right? I did not tell you this, but I hope that with our discussion, you can figure it out. So basically now you look at a function that is 3 variables, right? Once differentiable in time, twice differentiable in 2 space variables. What do? We look at the d of this function in the 2 Brownian motions. Yes, because that's what we're kind of dealing with here. Now, can anyone tell me how this would work?
would be ft dt,
Yes,
and then fx dwt1, fy dwt2,
yes.
and then f1/2 fx fy dwt1 dwt2.
Right, so you want a mixed term first, right? But if you want to do that, then the mixed term gets added twice, isn't it, Kareem? So you there's no 1/2 left. Yes, and then there's the second derivative term, which we call, right? You can do this, or you can call it the quadratic variation. Which basically, right, is just what? dt, right? And what is this guy? From your midterm? 0, right? So anyway, but here we can write like this, because if they are correlated, then they won't be 0, right? But anyway, what I want to say is, right, you see, if you understand the original Eagles framework, then extending it to further framework is no problem. Okay, so here, if you look at this, what is it, right? It will be 1 over, right, S1t ds1t minus 1 over S1t squared ds1t, right? Like that. Or if you want, right, let's just do S1t squared. This, I think, is more suggestive. Okay. Well, what is it, right? So you see that this will be just canceling all these things out, right? So it will be mu1 dt plus sigma 11 dw1t plus sigma 12 dw2t. What about the S1t squared? What that means is, right, you take this whole thing and then you square it. And you use the usual calculus rule, right? That dt squared is equal to 0. dw1 squared is dt. dw1, dw2 is 0, right? dt, dw1 is 0. So very quickly, you see what? The only thing left is sigma 11 square S1t square dt plus sigma 12 square S2t square. Sorry, S1, right? So what does that become? Mu minus 1, sorry, 1/2, right? Mu minus 1/2 sigma 11 square minus 1/2 sigma 22 square dt plus sigma 11 dw1t plus sigma 12 dw2t. Which, by the way, right, looks super similar to the Black-Scholes model, except that, right, now you subtract one more 1/2 because of the volatility, the secondary motion, right? So to return to our question, the average log return will be mu subtracting these two guys. But you see, again, right, in this way, it's actually consistent with the above, with the original framework, meaning that it's actually subtracting 1/2 volatility squared. Yes. So that's exactly the same thing as we said before too. Log return is different from percentage return on average by 1/2 volatility score, right? The rate. So same framework. You know what I'm trying to say? So I just want to say, right, that you could, right? I try to stay simple with the course, but you could, right, if you know the procedure, extend, right, what we do to further things. Any questions so far? So this is just trying to help you understand, right, the multi-asset model with multi-variable motion sources. Now, in connection with risk neutral pricing, right, what are we doing? In connection with risk neutral pricing, you see that, right, if you know what's going on above, and the same argument applied, meaning that for anything to be a martingale, when you discount like this, it better have a drift 0 and the rest being a martingale. Sorry, the drift being R, okay, and the rest being martingale. Why? Because the drift being R will cancel with the part generated by the discount. Yes, so the discount will cancel with the drift and leaving you with a martingale. Meaning that you can mechanically just insert an R here. Okay. Now, of course, right, you know, we start out with a mu1, right? We start with a mu1. So we need something like this, right? Sigma 1, 1, right? And I'll do this. S1T W1 plus theta 1 times T plus sigma 1, 2 S2 W2 plus theta 2. All right. Similarly for S2. This is your homework, by the way, of this week. Right. Sorry, this is S1 still, right? This is S2. Okay. By the way, this is not theta square, right? It's just theta 2. You can make a subscript if you want. So these are two constants, right? So by the way, right, let's see what's going on here. What's going on is I converted, right, the dynamics above to something where I try to force the drift to be R. The reason being the risk neutral condition that I said above. So of course, then, you know, the drift is not really R, right? The drift is mu1 here and mu2 here. So I need to compensate for it, right? There's some compensation going on, which, if you think about it, is tedious to think about. At least it's not immediately obvious. So what do? You just tuck it into some unknown. All right, you don't know what it is, but you will write down an equation that compensates for it. All right, that's how you think. You write down what you want. You write down whatever trash that is that needs to be compensated for, and then you will make the connection after. Okay. What else? The second thing I want to say, right, is that even though, right, these two assets are different, right, in terms of sigma 1, 1, sigma 1, 2, whatever, the theta 1 and theta 2 must be the same, right, in both assets. Why? Because they will be converted into W tilde 1 and W tilde 2, right, in the risk neutral model. So if you use different drifts here, then you cannot convert them in the same risk neutral. You understand what I'm trying to say? So that's why it must be the same theta 1, theta 2 on both assets. Got it? So now, can we do this? Well, the answer is right. We can, and exactly right. So now you can ask about arbitrage free and completeness of the model, namely the two asset model here. And then, right, you see it has to do with existence and uniqueness of risk neutral probability, which has to do with, can you define these guys? And can you define these guys uniquely? Which boils down to existence and uniqueness of theta 1 and theta 2. Do you understand? So now, right, it comes to a time where we have to see what these guys must satisfy. And that's easy because these guys must somehow compensate back to mu1. In other words, right, it will be r dt plus sigma 1 theta 1. Sorry, we only need dt, right? Plus sigma 1 2 theta 2 is mu1 r plus sigma 1 2, sorry, sigma 2 1 theta 1 plus sigma 2 2 theta 2 equals mu2, which by the way is a what? A lovely linear system. Right? So if you want, you can write something like this. Theta as a vector, right, is mu minus r times vector 1 times sigma inverse. Which, by the way, is what? Exactly the market price of risk equation for the multivariate model. It's a multivariate version of that. I mean, of course, right here, I'm already cheating. I'm assuming that I can write sigma inverse, but of course, right, you see if sigma inverse doesn't exist, right? So existence and uniqueness exactly has to do with invertibility of sigma, which is this matrix. And again, right, I just want to make the connection to arbitrage-free completeness, right? It will be super complicated for you to sit there and think, okay, does this model permit any arbitrage opportunity? Is it complete? Blah, 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 right? But now you know, right? And now here's where you have to rely on the math because it's not obvious to see it, with intuition. As long as this matrix is invertible, as long as it's not degenerate, right? Which also, by the way, makes sense. What does it really imply? What really implies is that, right, this is the driving force, right, of the noisiness of the stock. Being invertible means that fundamentally these guys are different, right? Why? Because not being invertible means what? Means that one row is a linear combination of the other row, or basically here is a constant multiple, right? So basically it says that if this volatility is a constant multiple of the above, for example, that means that these two assets behave exactly in the same way, in some way, meaning that, in terms of the riskiness, so there will be arbitrage. Is that okay? So lots of implication right behind this. Again, like I said, you can spend the whole class going through this kind of analysis, but here I just want to bring up this point in connection with risk neutral measure, change of measure, that kind of thing, right? And the framework. Any question about this? All right. Now, like I said, right, I want to make this class as practical as possible. But there are places where you have to go deep into a theory before you can come out and understand the practice, right? But here are some practical points, right, about this whole discussion. Not that so by the way, right, not that the above is not practical, but I would admit that, right, they are a little bit into the theory, right? But still, they are relevant. But here, right, here's why they're relevant. For example, the first thing is to prevent you from naively making some model that has problem. For example, could you do this? Sorry. So could you do a 2-asset model with one source of ground motion? Yes or no? Sorry, I would want sigma 1 and sigma 2, right? Can you do 2 assets and 1 source of noise? Did Fatima say yes, or that's a yes from a different question? Nope. Why? Because what will be your sigma matrix? Is this matrix invertible? No. Right. So, of course, unless you somehow make these guys equal in a weird way, so that, right? You can define one single risk neutral probability, but in general, if mu1 is not equal to mu2 or whatever, so in general, right, you cannot define. You should not be able to define a risk neutral probability. All right. Coming from sigma not being invertible. So anyway, right? So maybe I should do this. Maybe I should do this. It really comes from this. It's really the equation AX equals to B, right? So what we're saying here is that, right, you have more, you only have one source of noise. So basically you have, sorry, yeah, you only have one source of noise. So what do I want to say here? You have you have a skinny matrix, right, with only one variable, right? So that won't work. Okay. So basically, I forgot, and we don't need to go deep into it, but basically, when you look at a linear system like this, right, the number of unknowns and the number of equations must be balanced. So basically, here you will run into some issue. Okay. And the other way also is similar. So basically, I want to say is the rule of thumb. This is actually the worst case. You want the source of noise to be at least as much as a number of assets. Okay. Again, right? Because in a skinny matrix, right? This is an overdetermined system. Yeah, I remember now, right? If A is skinny, then you cannot have a solution in general, right? When A is wide, then you have non-uniqueness, which is more tolerable, right? You have existence, you just have you don't have uniqueness. But when you have a skinny condition, a tall matrix, then you have overdetermined system. Yes. And so rule of thumb is if you don't care for existence, if you don't care for, right? So we'll look at that later. But number of source of noise, if you have less source of noise than assets, then you will run into arbitrage issue. So here, the model is not arbitrage free. So why do I say this is practical? That tells you that when you construct multi-asset model, you better check number of source of noise, and you don't want to kind of have less, right? That's the one thing that you just do right away. Now, let's look at the other slightly extreme, right? Where you have two sources of noise for one sock. Not extreme, but the other case, right? Okay. So one asset, right? Two nodes. Is this an issue? Is this a problem? What happens here?
I don't think it's a problem, but can't you just simplify it? Because you have two.
You cannot, Kareem, in this way, right? I think you want to combine them into one, right? But you cannot combine them into one single prime motion. In other words, this model is fundamentally different from, let's say, this model. You know why? Because you cannot factor these two and then combine them into one single normal, as far as I can tell. I don't think so. Wait, can you? No, actually, I take it back, Kareem. You're right, you can, but qualitatively it's different like this. Qualitatively it's different because here is easy to show, right? Again, suppose you want to look at risk neutral, right? Then you do this. And then you have, right? This, right? Sorry, times t, not sub t. Yes. Then what equation must satisfy? R plus sigma 1 times theta 1 plus sigma 2 times theta 2 is equal to mean. How many choices for theta 1, theta 2? For infinitely many, right? So what's the issue? The issue is this will always be arbitrage free, but it will not be complete. Meaning that if you try to price this, you have many ways to price an option on this model, and they're all consistent. All right. Again, we can go deep into that and make the financial connection. It's interesting. I don't think we have time for that. There are more things I want to discuss about. But the implication here is that there's no unique price for an option based on this. In other words, if you have a call option based on this model, then you have a million prices depending on what kind of risk neutral probability you want to use. So there's the quote problem in that way, right? But let me tell you that again, from the pedantic point of view, this is more tolerable, meaning that it's at least you can work the model, you can have a price, right? The above model, the above situation, you can't even have a price because your model is faulty to begin with. You allow arbitrage, right? Here, you can work with things. It's just that you don't have a unique price, depending on what risk neutral probability you use. Okay. But again, right, so I want to say the practical from that point that when you model asset, there is a balance between source of noise and number of assets if you want your model to be perfect. Otherwise, you run into a problem. And you want to be aware of the case when the source of noise is less than source of assets. Okay. Questions so far? So, right, let me say this, no unique price. So no unique risk neutral price, all right? So our model cannot spit out one single price. That doesn't mean that if you trade this on the market, it won't have a price. Well, that's a different story. Okay, the second one is probably a little bit more tolerable than the first one. The second one is an interview question. And this is something that I did really get asked at one point from Goldman Sachs, if I remember correctly. And the fact that I'm not in Goldman Sachs right now tells you that how well I did in that kind of interview. But anyway, right, what is it? Here's a question, right? And I think it's very routine. You can expect this in any kind of quant interview that you go to, kind of, I think. First of all, right, they say, well, you go to math finance and that kind of thing, right? So tell us about Black-Scholes model and Black-Scholes formula, right? which, by the way, right, if you fail here, probably you will have no chance, right? So you do blah, 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 and you say, you know, S0, sorry, V0, right? S0 ND plus minus K e to the minus RT ND minus, right? So of course, right, I mean, like we'll talk about call option, blah, blah. So yeah, okay, fine, right? You know your stuff. Can you show us how to derive the formula? By the way, I did not get asked this question, but if you went to the seminar where Sherry Zheng, right, talks last semester, she did say that she got asked this question, yes, on her interview. So I guess people do ask this question. By the way, right, just a personal point of view, I don't think anyone can reasonably derive this cold, meaning if you have no idea what's going on, it takes you at least an hour to even see what's going on, right? Even I cannot do this cold. But what you want to do here for this kind of weird question is have an idea of the steps, right, that can simplify the calculation for you. Someone asking you this probably have no interest in seeing you do all the calculus all the way down. But as long as you say, okay, here's how we simplify things, right? We would start out with probably something like this, right? And then we would probably even simplify it further by calculating something like this, and then show them how you do it. I feel is adequate. At least, I don't know, right? Again, full flash, Black-Scholes derivation is a boring business no one wants to watch. And by the way, I think your homework, right? Homework 1 or 2 was kind of telling you how that simplification process goes. Anyway, right? Okay, suppose you went through this step. The next one actually is the meat of the question. Tell us what ND. So by the way, right, people do call this ND1 and ND2, by the way, right? I just call ND plus, ND minus, and some people do call ND plus, ND minus. But tell us what ND plus and ND minus mean. Okay, and this is the meat of the question. And there you go. What do you think? What do they mean? Definitely not good enough. Yes, definitely is a CDF, but that's not what they mean. That's what they are, right? You're saying that NX is probability standard normal is less than or equal to X. Okay, at least you know what that is. That's not what they have in mind. They have much further thing in mind than that. By the way, right, this is really, I do believe they are popular interview question. Because they want you to understand, see if you understand what you're doing, right? Which I would admit is hard, right? You get shown a lot of math, a lot of knowledge, but at the end of the day, right, like I said, and the practitioners also have this point of view, you want to take a step back and wonder what the heck you're looking at, right? It's not a bunch of math, a bunch of formulas, because any monkey can look at that and do that. As an intelligent quant or human being, you want to look back and say, well, that makes sense. I understand it this way, right? You don't have to do it exactly, but you must get a meaning. So here's the meaning. Anyone wants to try before I give you the answer? So the meaning actually has to come from the pricing equation. In other words, it starts with the basic. You start out with this. All right, because after all, right, that's how you derive this to begin with. So actually, that's how you went from A to B. But, right, here's where you do not do the dirty calculation, but you look at the structure thing. Oh, sorry, it's a plus, right? And the structure of thing is this, right? You convert the plus into an indicator function, which again, right, you would have done going from step A to step B anyway, some implicitly, explicitly. But you do not write down the calculation, as I said, but just split this. Okay. And now you compare it with this. Right? Because after all, that's what it's supposed to be. Okay. Does it look better now? Now, can you tell me at least what this guy means?
That's the expected value that you're gonna end in the money.
You almost get there, Kareem, but you did not say the right word, right? It's not the expected value, but it's the probability, right? Because it's an indicator function. Notice I use all English to explain it, which is actually probably what they expect, right? You word advice, right? On an interview, especially on a phone interview, do not say anything like e tilde like blah blah blah. No one will understand what you're talking about, right? Without something in front, right? Imagine if I lecture to you like this without any screen, right? Who would know what I'm talking about? Of course, except something like this where everyone memorizes formulas, so you could say it and people would know what you're talking about. Besides that, English, right? So you could try to explain this verbally, but in the end, right, notice everything in English. Also, keyword risk neutral probability. If you just say it's the probability that blah blah blah, who knows? Some guy who doesn't have a good day might tell you that's not right. You missed the word risk neutral. Why? Because risk neutral and physical are two different things. If you don't distinguish that, again, right? Someone may say, yeah, it's fine. Someone may say, you don't know what your stuff. All right. But that's the whole thing. Because that's the easy part, right? That's what everyone should know. That's not the part I want to talk about. The part I want to talk about is ND plus. All right. What's ND plus? It's probably unfair, right, to ask you this because we haven't covered this, but it's kind of connected in this way. And I want to tell you right now, it's also the probability that the call option expires in the money. And you say, what? Right? There's a whole bunch of things here. What are you talking about? Of course, the catch is that's under a probability, or rather under the probability resulting from the change of measure using S as numerator. All right. So the last bit is something that you haven't seen, so I say that's unfair. But we'll get there, right? This will probably this last part of the class is going to be on foreign currency. Anyway, right, or foreign exchange rate. But at least you see the change of measure. change of measure, right? It's there, right there, even in the Black-Scholes. How? How is this, right? If you look at this, right, these guys are these guys are equal, right? So actually, you should have it, it is technically this. Right? And so, what is this? That's your ZT. And that's your X. And so that's why, right? It's not risk neutral probability, but it's a change of measure further away from risk neutral into another probability. You understand? So that's the answer. It's really the answer. All right. But so that's practical in that way, meaning that, right, the change of measure framework is not some exotic framework where we discuss, well, existence uniqueness is right there, even in the Black-Scholes. And people can ask you this on the interview. Okay. Any question? Last part, right, which is connected to this. The last application is something like this too, which is coming up, is the exchange rate model, FX. FX stands for foreign exchange, right? I'll just tell you very quickly what happens. In the foreign exchange rate model, we will need two things. One is the dynamics for the exchange rate. And one is the dynamic for the stock. So what's the idea? The exchange rate, right, will be something like, I believe, right, this is like price of euro, dollar per euro, right? Let's say. So what that is right, of course, the price of euro in dollars, right? The price of euro in dollars. So anyway, the story will come up where it's at some point, right, you want to do something like this. Maybe not this, but maybe this. Right, I'm writing something here that may not be completely correct. I mean, completely precise. But basically what you're doing, right, and I think I need something like this here. Basically, you're looking at a call option, right, of a US stock, take Google, but you want to convert it back into euro, and you want to discount it using the euro risk-free interest rate, right? So I think, oh, wait, hold on. Anyway, something maybe off. I think it should still be R here or something. Whatever. The point being is this, that when you do something like this in the calculation, you are effectively doing a change of measure. Why? Because this guy right here, right, will be your ZT. Okay? You are converting from the framework of the domestic risk neutral probability to a foreign risk neutral probability, right? You're looking at the European market where their denomination, their money, their currency is random because of the random interest rate. Sorry, random exchange rate. Okay. So anyway, right, do not worry too much about the precise math because I'm not teaching you this right now. But just to tell you that the whole foreign exchange framework, which is connected to the concept of numeraire, is very standard if you want to model, right, assets in foreign exchange. So there's this whole topic that entirely relies on change of measure in a very practical way, because that's how you do model, right? It's not even abstract in the same sense of risk neutral. It's right there, right, in the model itself. Finally, right, something that we don't discuss in this class, but is also very practical, is the idea of, right, and I think Cesar mentioned this, right? Use change of measure kernel, use change of measure to make multicolor simulation more efficient. Right? And the idea is, right, suppose you want to calculate some expectation, but this guy has very high variance under your original probability. You want to switch to something else and deal with a different random variable, but right, hopefully that random variable has lower variance under the new probability, so that it allows you to calculate more efficiently, right? So importance sampling, as Cesar discussed, right, is one easy example of that. You know, hopefully you learn that with Casper, right, in computational finance. But again, right, that's a more advanced computational technique that definitely does not fall under, right, our discussion. But I just want to say, right, the concept of change of measure in general, and that's why I spend more time on it, it's not just, you know, abstract pedagogical discussion. It has a lot of applications in many places, right? So you want to kind of at least understand what it's all about, right? You may not get the whole mechanics, but you must understand at least the idea. All right. Okay, so that's all I have for today.
Thank you, Professor.
Yep, sure. All right. Any questions? If not, yeah, sure. I'll see you next time. Yeah, sure. Oh, by the way, remember there is a seminar, all right, at 5 p.m. Oh, for our student, not for you. For the student in the program, it's like we bring in practitioners and ask them to talk to our students about jobs, experience. Sometimes alumni come in and give some talk, that kind of thing. So that's that kind of seminar. Mhm. All right, see you. Yep.